Hello everyone, welcome to Computer Science E1. This is Lecture 5, Multimedia. And so I know everybody is bleary-eyed from their days on the beach after spring break. And so I thought that to begin, we would start with a fun animation representing multimedia. Uh-oh, I'm going to have to plug this in. Hold on. Let's see, here. Now this would be very easy to just sort of look around on the internet and find funny things and show them for the entire 2 hours, but this does actually have some relevance to some of the things that we need to talk about today. And so in particular, this animation that you saw represents a certain file type, or it's made from a certain file type called Flash. And so many of you have probably seen Flash, even if you don't know, and you've probably heard of it perhaps, even if you don't know exactly what it is. But Flash is basically just a plug-in for browsers on the internet, for browsers on your computer more specifically, that allow you to display various types of files. And this is just one of them, which includes animation. And so traditionally Flash was used for a lot of animation and a lot of what are called vector formats, so something like that looks like this. So what might look a little bit different as opposed to the previous animation that we had seen, besides obviously the content itself, is how it is actually drawn. And in particular, if I resize this page, we can see that even though it resizes, what happens is that the lines that make up these horses do not actually become pixelated. And so this is yet another type of Flash example. And so basically what you do with this one is, this is an example of interactive multimedia, where it not only includes sound and animation like we had seen before, but also what we can do is now click on each of these horses to be able to get them to do something. And you can witness my terrible timing as I try to get everybody aligned properly, and eventually what you get is this very nice, I know it's horribly off, but that's the downside of live demos. But what's more interesting is as we scale this, as we change the size of this particular window, it doesn't actually impact the sharpness of the image that we're looking at. And this is in stark contrast to pretty much everything else that we see on the internet. And so just this other Flash animation, for example, what you saw was it was basically this, this collection of palettes and windows in a Microsoft Word style or Adobe Photoshop style application, and you could see the pixelation from each of these things. So let me point out now, if we restart it from a specific point, look at the left side how you can start to see individual pixels. And what a pixel is, and I can zoom in even more to make this even more apparent. What an individual pixel is exactly this. It is just a small square representing some color that you can see on your screen. In fact, your screen is made up of thousands of these small pixels. And so we use the combination of pixels not only to make the elements that we see on screen, but we also change them rapidly like this so that it forms this illusion of animation or motion like what we can see. So there's this important distinction then between different types of files. One of them is this so-called bitmap, where when we look at an image and it's made up of individual pixels, there's a limit to how much we can zoom in on that image before we start seeing the individual pixels. And this is compared to, let's see, I don't know if there's a way I can pause this. Compare this to a vector type graphic where you can then use any resolution and it still looks just as sharp. So if we were to zoom in on this as much as we possibly could, what we would start to notice, let's see, I don't know if this is, nope, it's not working, but as I resize this window, as we saw, it doesn't matter what size it is, it still appears to be sharp. There's no noticeable pixelation in the horses. So this, again, is two distinct types of files, two distinct ways that we can represent graphics. One of them is this vector format, like we can see here, and the other one is this bitmap format. And I mentioned before that there's this plugin called Flash, and Flash does a whole lot of things, but it does actually include capabilities to be able to display vector formats like this and animate vector drawings, but also it can display bitmap images. So when you go to YouTube, for example, and you try to display a video, by default it loads a Flash player, and that shows you a bitmap image. It is just a movie that is made up of multiple bitmap images. And so you work with, this is not, although this terminology might be new, these types of files are not new. In fact, you work with bitmap files almost every day. And so when I say bitmap, realize that there is actually a file itself that is called a bitmap type. And yes, that is a type of bitmap file, but what I'm talking about is more general. This actually applies to pretty much anything that just makes up, through the use of rows and columns of pixels, the end result is just an image. And so this is, in effect, a bitmap image. And when we zoom in on this image, we can see that it is, in fact, bitmapped because we can start to see pixelation. We can start to see individual pixels that make up this particular file. And so this is an important distinction between bitmap and vector. And most of the time, when you're working with images, in fact, almost all of the time, you are working with bitmaps. If you're taking a photo with your digital camera, for example, that's taking a bitmap photo, even if it's in a different file type than bitmap. If you're looking at a video online, for example, most likely is it going to be the individual frames are going to be bitmap images, just because the combination of them is sort of the easiest for us to do. So the difference between each of these is that bitmap is basically, it's what it sounds like. It's just a map of bits that make up all of the pixels that we see in an image. So it just is this, a rectangle full of pixels with different colors. And there's a maximum limit to how much we can actually zoom in on this bitmap before we start seeing the individual pixels. Now, what's different about vector formats is that those actually use mathematical equations in the format to describe how this line should behave. So it says, okay, this is actually going to be a straight line going from this point to this point, and because it's mathematical, then they can just recompute what the line should look like depending on the resolution itself. And so there's this resolution dependence versus resolution independence. There is this idea of resolution dependence in a bitmap where it depends on the resolution that you are looking at it to see if it's going to be a sharp image or not. Whereas, and compare this again to vector images where this is resolution independent, because it doesn't matter how high of a resolution you make that image, it is still going to be sufficiently high that it's going to be sharp, just because the mathematical equations then describe how this particular image should work. And so it's it's much easier for us when we're thinking of digital cameras and all of these things that actually make images. It's much easier to think of them in terms of bitmaps, just because it's much easier for us to define individual pixels, the color at each individual pixel, and this makes a lot more sense to us rather than using some vector format. And so though it is definitely possible, if you use something like Adobe InDesign, for example, you can actually create some vector graphics so that they can scale up to be absolutely humongous without any loss in quality. Most of the time, that's sort of kept to things like short animations like the horse one that we just saw, and also to things like logos, where resolution independence is actually very important so that we can scale the size of a logo very independently. Bitmaps, although it's very easy for us to do, we do have this, this limitation of the resolution. And in fact, you're familiar with these sort of connotations of resolution that a lot of digital cameras actually use, like megapixels, for example. That actually describes how many pixels an individual image might have. So if a camera says that it has 8 megapixels, for example, that's just saying that the number of pixels in width times the number of pixels in height, that's the total number of pixels in this entire image. So if you have 8 megapixels, then most likely you have a camera that's something like 3,200 pixels across by 2,300 pixels down, or something like that. And that actually describes then the size of the image. And if you try, you can zoom into that image and blow it up to be 100%. And if you are looking at an image that is 3,200 pixels across by 2,300 pixels down on your own monitor, then most likely that image is going to be larger than your monitor. So we're talking about pixels. So keep in mind that pixels sort of are this universal way of describing a dot on a computer screen. And so we can describe not only a pixel in an image, in that an image is made up of multiple pixels, but also projectors or screens are actually made up of pixels as well. In fact, we can see the resolution that the current screen is operating at, and that's at 1024 by 768. So what this is telling us is that there are a certain number of pixels on this projector display. There's 1024 across, and there's 768 down. So if I am looking at this image, this 8 megapixel image that was something like 3,200 pixels across by 2,300 pixels down, and I look at it at full size on this display, how is that image going to appear? So I'm just displaying this massive image on the screen, and how might this look to us? So yes, we will see it completely zoomed in at 100%. So each individual pixel of our screen matches an individual pixel on the image itself. But there's something funny here. There's a difference in the number of pixels. So what does this mean? What is our computer going to display if we try to do this? Any ideas? So it's not going to compress it, you're just going to see however much will fit on the screen. So in essence, you're just going to see a small fraction of the actual image. And so there's this idea of scaling. So what we tend to do by default when we're working with computers is that we like images to sort of be as large as possible. So what we might do is we might resize the image to be smaller on the screen. And so what that means is that we're taking this absolutely huge image, say 2,300 pixels, or no, rather 3,200 pixels across by 2,300 pixels down, and we're resizing it. We're making it a little bit smaller so that it now can fit within the resolution of our screen. And this is an important thing to realize, that there are, in fact, pixels, and we can call pixels the same thing across a multitude of formats, but there's this additional level of scaling that tends to occur whether or not we are zooming in on something to make it appear bigger, or we're zooming out, so to speak, to make it appear smaller and to make it fit within our screen. So zooming out on an image, it's not really going to impact our resolution dependence all that much, right? Because if we're zooming out, then the pixels in an image are perhaps a little bit smaller. And so in essence, we have enough pixels to display everything that we want to. So in essence, this image here was taken with an 8 megapixel camera. But this is the entirety of the image. And so in order to fit it on this screen, this is just like what we had talked about, it had to be resized down. It had to be scaled down to fit the screen. Now, there's nothing particularly complicated about this concept. We're just sort of trying to formalize some of this terminology into scaling and resolution dependence and these sorts of things. And it does actually build to some important things that we'll get to in just a moment. But right now, I just want to mention all of these things because it is, in fact, important. Now, if we go the opposite direction, let's say that we zoom in on an image so that it's at 100%. And what that means is that one pixel in the image matches one pixel on our screen, and that's sort of the ideal resolution. In other words, that's the highest resolution that we can get before we will start getting blockiness or pixelation. Because as we zoom in more, that same pixel in an image has to become bigger and bigger and bigger so that we can continue zooming in. And so this is, again, what we're seeing here. We're just zooming in on an image so much that we are just seeing the individual pixels that make up that image. Yes? So if we have an image that's enormous and we're trying to fit it on the screen, does that entail compression? So yes and no. So if you're just looking at an image and you zoom out on that image, then perhaps what's going to happen is that it's just going to resize that image and no recompression. The image itself won't be modified. But if you're actually modifying the image, let's say you open up this image in some software like iPhoto or Photoshop or some other image manipulation software, and you actually tell this software to resize the image, then it's actually going to do that. It's actually going to resize the image so that it becomes smaller, and it's going to then cause the file itself to be smaller as well, just because there's fewer pixels in the end result. And that sort of thing can actually cause a recompression when you're actually saving the image. But we'll talk more. So it is in fact independent of resizing the image. But as a result of resizing and then saving the image, can we be compressing it? So strictly speaking, I would say that no, compression is not necessarily making it smaller. Compression is talking about something a little bit different. That deals with not the size of the image on the screen like this, but rather the size of the image on disk. How many bytes does it actually take to store this image on a disk? That's usually what compression refers to. We will actually talk about compression and the different types of compression in just a little bit. Okay, so we have this image, and we can blow it up to some enormous quantity like this. And I have to say that there's a lot of TV shows and movies out there whose entire premise is based on the fact that you can zoom in on an image like this and enhance it so that you can see all of the details. And frankly, that is just total crap. Every time I see that, it bothers me to no end whenever they zoom in on some image like this and they say, enhance, and then they can see the reflection of somebody's face in this little thing. There's no way that you're going to be able to do that because this is the entirety of the data that this file has. What you see here, that's it. You're going to be able to guess as well as a computer what the higher resolution version of this dot, whatever this is actually going to be. And in fact, if we see where this is coming from, we can see that this circle is pointing out this small circle up here, which is basically just an imperfection in the wall. So it's really just like a bump or an indentation of some kind that exists in the wall itself. And so this is not going to provide any useful details, but the concept is the same. It doesn't matter if you're taking some really low resolution photo of somebody's, oh my gosh, why am I blanking on this? On somebody's license plate. That's the word. So it's not like you're taking some really low resolution photo of somebody's license plate and then realizing, oh gosh, okay, well now I can just enhance it. That's just not going to work. And there's been quite a bit of research that says that, okay, this might actually be possible, but realize that that also is not, it's not exactly what you would think of. There's been some recent research that came out a couple of years ago that said something like, well, we can actually recreate an image based on just a few pixels at a time. But really, if you read the fine print of this, it means it said that it can recreate the image with high probability, but if only you had random pixels from various points within the image, not if you have something like this, some uniform collection of bitmaps. So in short, this enhanced stuff, it's just a bunch of baloney, and it's not really worth anybody's time to realize that it's going to be useful. Now, there is this concept of sharpening, which is actually a valid concept, which what it does is it takes an image that looks like this, and it might be pixelated, and it tries to make it look a little bit smoother. It tries to sharpen the edges a little bit, just so that it makes it look a little bit more pleasant to our eyes. Now that actually does exist, that technology does exist, but it doesn't actually give you any additional information. It's just a trick, it's just sort of an optical trick to get our eyes to make it appear as though it is a bit better or a bit smoother, even though there's not actually anything that's more enhanced about it. Yes?
This is a big jump, but when you were talking about this as
Uh-huh.
And how when sometimes older recordings are being cleaned up,
Mm-hmm.
supposing you taking pops and cracks and junk out of them,
Mm-hmm.
I mean, there's no way to restore missing sound into those recordings. So, I mean, to my ear, often when I heard these pre-engineered things, it just sounds like kind of softer sound,
Mm-hmm.
like cotton balls.
Okay, right. So,
That makes any sense. So is there something analogous?
yeah, so in fact,
A little bit unreal?
so I'm less familiar with sound engineering than I am with images, but the concept is pretty much the same. In sound, you have a finite amount of data. You have however much your recording has, that's how much data you have, especially if it's digital. If you have some digital file, some digital representation of that, you're not going to be able to get any additional volume out of it, or rather, any additional resolution out of it. So if it's some orchestra playing, for example, and you hear sort of a faint sound in the background, you can probably adjust the volume to see if you can hear it better, but you might not be able to fully understand what it is if it's very, very faint. And so when they're talking about cleaning up audio, especially old recordings, and removing the pops and the hisses and that sort of thing, as far as I know, what they're doing, and there's probably some sophistication involved that I'm not very familiar with, but I'm sure what they're doing is they're looking at the sound and figuring out what it's supposed to sound like, because perhaps they know what the progression of notes might be, and so they might be able to recreate that progression of notes within a sound. And so it would be sort of similar. I think the analogous situation to images might be if you have an old image, for example, and let's say a corner is torn off or burned off or something like that, and you want to recreate the original image, you can go based on context and figure out what might be in that corner, and an artist might be able to recreate what that image probably looked like, but it's not going to be the original, even though it looks very good, and even though it's almost perfect, it's not quite the original, if that sort of makes sense. And so I think that might be the closest analogy to sound engineering in this respect. Now, so when we're talking about, so we mentioned enhance, for example, and how we can try to blow something up as big as possible, and we're not actually going to get any additional detail out of this. But let's go back to this idea that we don't have this capability. There's no way that we are going to know what the original detail was. And this is certainly true. But we can get another couple of interesting tidbits out of this image just from looking at this blown up portion of the image. So first of all, realize that we can see the individual pixels, but that each pixel has its own color. So somewhere there is some way of defining the amount of color, or which color is actually going to appear in an individual pixel. And this is very much like, you can think of this very much like, well, it is what it sounds like. It's a bitmap. What that means is that for each pixel, there's a couple of bytes of information describing the color in each individual pixel. So for each pixel that you see here, there's about 3 bytes of information defining the color that makes up this information. And how do I know that? Well, most of the time when we are talking about colors and images, it comes in a variety of formats. It might come in, say, something like 8-bit, might come in something like 16-bit, or even 24-bit. And what this means is the number of bits that are provided to each pixel to define the color within it. So if we have 8 bits of color information, that means we have how many bytes per pixel? Yeah, 1 byte per pixel. And so 1 byte represents how many distinct values? We talked about this. So if we have 1 byte, then we can have how many different? 256. Right, 256 discrete values. So if we have an image that then has 8-bit color, for example, then what we are saying is that that image, at each individual pixel, we can only have one of 256 different colors. And this is not going to be very much, right? We will actually be able to look at an image, especially if it's of a photograph, which has maybe thousands or even millions of different colors within it. We can look at a photograph that's made up of 256 images. We can realize that that's not enough. It looks funny. It doesn't look like there's quite enough colors there. But there is other bit depths available, like this 24-bit bit depth, for example. This means that we have 3 bytes of information. And so that's 256 values times 256 times 256. In essence, we have, I think, 16.7 million different values available to us for each individual pixel for different colors. And so how is this broken down? Well, realize that when we have 8 bits of information, or rather 24 bits of information, it's broken down into primary colors. And it's not the same primary colors that you might have learned in elementary school, but instead it is this common set of primary colors that computers tend to use very frequently: red, green, and blue. RGB, and in fact you might have seen RGB in use in a variety of contexts, and it's true pretty much any time there is a computer or some computing device that has to display colors. So TVs, for example, this applies to especially modern TVs that have pretty sophisticated electronics. Computers definitely use this terminology, all sorts of stuff. So we have 3 components: a red, a green, and a blue component, and each one is allotted 1 byte of information. So what this means is that for each of these 3 colors, we have 256 discrete values. This may not sound like very much, but remember, putting all of this together, if you multiply 256 times 256 times 256, you get millions of different colors. And in fact, again, this is something that if we take a look at our monitor, this is something that translates relatively well. So let's see, I'm not sure it's on this screen. If we go to color here, we can see it's not on that one, it's on this one. No, where is it? Oh, they must have removed it in this version. So, okay, so my live demo is now a year old, but typically when you look at the display options for a computer, it actually tells you what the bit depth you actually want. And in Macs older than this one, it would actually display thousands or millions, and most of the time millions would be displayed. And on Windows computers, usually it tells you something like 8-bit versus 16-bit, or thousands or millions, or some similar thing, and that's basically referring to the same thing. How many bytes are you allowing in each individual pixel to make up all of the individual colors that exist within an image? Yes? What is the Hertz rating measuring? Yes, so a Hertz is basically something that occurs every second. So you might have also seen Hertz in the context of CPUs, because CPUs will do something in, say, gigahertz, and so billions of hertz or millions of hertz, depending on the age of the CPU. In this case, this is how often the screen is refreshed. And so right now, our eyes have a minimum limit below which, if something is refreshing at a lower limit than about, I think it's 15 or 16 frames per second or so, 15 or 16 times every second, then we will actually be able to notice that there is some refreshing going on. It won't appear smooth. The motion won't appear smooth to our eyes. So generally, the sweet spot is something like 60 hertz or so, just because that's refreshing fast enough for our eyes to make it appear to, or for it to appear to our eyes that it's this smooth motion. So just like movies and or pretty much anything where there's recorded motion going on, what we're seeing is not, in fact, very smooth motion. It is, in fact, made up of perhaps dozens of individual frames in each second. And so that's basically all that this refers to here. And so you'll notice that we can, in fact, increase the hertz, but you're probably not going to notice in this case, just because there's not motion occurring on the screen, and so there's really no reason for you to notice much of a difference in the hertz in this case. Okay, so coming back to this. So now we have this image, and I mentioned before that we have an image that's about 3,500 by 2,300 pixels in size. And so in grand total, it's about 8 megapixels, right? So 8 million pixels in total made up this particular image. But now I'm telling you that in addition to that, for every individual pixel, we actually have 3 bytes of information for all of the colors that we can represent. So what this means is that for every pixel, there's 3 bytes. So if we have 8 million pixels in this image, times 3 bytes, how big do we expect this image to be on our computer when we're actually writing it to the hard drive? 8 million times 3 bytes is 24 million bytes, right? So if we can do some division and realize that that's more or less about 24 megabytes, right? And so that's generally what a totally uncompressed 24-bit color image is going to be on our computer. It's going to be 24 megabytes. And that's pretty big. That's a pretty big file for something that's relatively simple, at least in terms of modern day multimedia, where we have sounds and images and motion and all of this stuff. So obviously, like we'd mentioned before, there's some compression going on to be able to make this image quite a bit smaller. And in fact, every time that you take a photo with your digital camera is actually performing some compression for you, so that it actually will write a much smaller version of this file. It's compressed. It's not resized. This is, again, goes back to this concept that we were talking about before. It's not that it's necessarily resized. It's that just it's using fewer bytes on the digital camera, or on the camera's memory, more specifically. So if we have now a digital camera, so realize that a digital camera is basically made up of a sensor that's included in the back. And there's a bunch of mirrors that a digital camera might have. And in fact, this is sort of a fancier SLR camera. So it's not something that you would have, say, in your camera phone or even a small point and shoot. But this is sort of the type of camera that people tend to associate with professionals or advanced amateurs, that sort of thing that you would go out and spend quite a bit of money to purchase for one of these SLRs. But once you get past all of this stuff that's in this camera, it is in essence just a sensor in the back that is made up of individual pixels that read the light that a scene has. And so this light is then captured by this sensor and converted into this digital format, where it is then saved in this sort of bitmap type file. So I mentioned before that bitmap is a type of file. It's not necessarily the file type, and I'll talk more about the distinction in just a few moments. But realize that when we take the photo, this camera then converts all of those individual pixels to some gradient of color based on this same idea, where red, green, and blue is broken down into, or each of the colors is broken down into individual components involving red, green, and blue, and then saved in its memory. And so there's actually, digital camera is actually a pretty sophisticated device, and it's in fact quite a bit more complicated than this. And in fact, the digital camera sensor itself cannot actually see color, in essence. So it is, all digital cameras can see black and white. And so you might be saying, okay, well, that sounds like the stupidest thing I've ever heard, because obviously I can take a picture and it's in color. Well, realize that the designers, the first engineers of this, realized that they could do a trick so that they can make it appear as though a digital camera can see color. And in essence, what this means is that for each pixel in a sensor, there's actually a filter on top of it, a red, a green, or a blue filter that's on top of that pixel, so that only that color will pass through to that pixel. So that even though that pixel is then only able to determine light from dark, it's then able to know, based on its placement underneath this filter, which is called a color filter array, just as a sort of the terminology for this particular type of filter. So this color filter array then filters the color into brightness that each individual pixel will then be able to monitor. It then will know what the brightness level is, and then in the end result is giving you a nice color image using these breakdown values of red, green, and blue. And so this is not something, it's so low level enough in the digital camera that it's really not anything you're going to be able to notice. Even when you use the silly black and white modes in digital cameras, it doesn't even remove the color filter array. In fact, it still uses it and then converts it to black and white later. There's a whole bunch of really interesting things, I think, and we actually go into quite a bit of detail. There's another class, so if you'll let me just blab a little bit about it. There's another class, Computer Science E7. If you're interested in digital photography, that's the way to go. We go into a lot of detail about cameras and how they work, and why megapixels is not the end-all be-all monitor of performance in a digital camera, so on and so forth. Might be something that you are interested in. So a digital camera then, when it takes a picture, can basically record essentially the most common, or two distinct file types. And so most of the time it will save a file in, say, the JPEG file format, but there's also another type that's much more ambiguous, called the RAW file type. And the RAW file type will actually save all of the raw bytes, all of the individual raw bytes that make up the image. And so when we were talking before about how an 8 megapixel image might be something like 24 megabytes, it could actually in fact be quite large because there's not much compression that happens in a raw file. Now this is a little bit of a lie. It's just that it happens to be a different type of compression, but I'll point out the difference again when we start talking about compression in just a moment. Whereas JPEG is the much more common version of a file type that a digital camera will write, and that is pretty heavily compressed. It actually will take an 8 megapixel image, bring it down to something like 1 or 2 megabytes in size, which is just a small fraction of what the original data actually was, but because the compression is relatively smart, it doesn't actually appear to us that there's any loss in quality. Even though there is in the background, they had to throw away some of this data. Now to compare this, once again, to bring this full circle to what we were talking about early on, we mentioned before about how there was this concept of vector graphics, about how there's these graphics that even though they look like they're made up of individual pixels, and in fact they are. When they're displayed on the screen, they do in fact have to be rendered. They do actually have to be displayed as individual pixels, but as we zoom in on on a small portion of a vector graphic, the computer is then able to recompute what it should look like based on how far zoomed in you are. And again, because it's just made up of mathematical equations, it really doesn't matter how far zoomed in you are. You can just see that it looks sharp. And in fact, you can see these sorts of jagged edges, perhaps where somebody was trying to draw sort of a smooth edge here, but in fact was just had a little bit of slop on either end. And this isn't necessarily a problem with the vector graphic itself. It's just the way that it was designed. It was just designed to sort of look like this, sort of cartoonish. And on the right, you can see this same image before all of the colors are put in. So just we have these mathematical equations that define this outline for this image, and then we can use more math to say, okay, well, all of this color that looks like this should be in here, for example, and just display the color within some geometric shape and display that within this image. And so if we have an image, and so we've talked about how if we have resolution dependence, so if we have an image that is in fact a bitmap, and what we want to do is actually blow it up so that it's a very large size, generally what we have to do is have a very high resolution image. So what we're saying is that if we have an image that is going to be a bitmap file type like this, and we want it to be absolutely massively huge and still appear sharp without any noticeable pixelation or any sort of problems like that, then we have to have a very high resolution within this image. And so this is where this sort of idea of having high megapixels has really sort of taken off, and that, okay, I have way more megapixels now on my camera, so now I can really blow up my image to be absolutely massive, and I will have great resolution out of it. And yes, that is true to a degree, but also realize that there's a lot of additional complexity in a digital camera that can define whether or not the number of megapixels that you have in that camera are actually of high quality, as opposed to, so quality does in fact matter for these individual pixels. But if we have to create something like a very big billboard, for example, and this is going to be dozens of feet wide perhaps and dozens of feet tall, or if it's just a standard billboard and it's dozens of feet wide and perhaps just a dozen or so feet tall, then ideally we would need to have an image that is very, very high resolution as well. And so we might say then that using something like a vector graphic would be ideal for this. And in fact, this is why, one of the reasons why it's very ideal to make logos or other designs that are meant to scale to be very, very large in vector graphics, just because then you don't have to worry about pixelation. You don't have to worry about blockiness as you zoom in on an image or as you blow up this image to make it much, much larger. Now, it's sort of a white lie saying that we have to do this for billboards, because there is another factor in resolution as well, and that is how far away you are from the object that you're viewing. If you're very, very far away from it, then we can only see, it's as if we have pixels in our eyes as well, and they're only, high enough resolution to be able to capture a certain number of things. So billboards actually, though I use that as an example, it's not strictly so that it has to be such high resolution, just because generally when you're viewing a billboard, you are many, many feet away. And so when you actually approach a billboard, it can actually be made up of pixels that you can actually see once you're close. But this is sort of analogous to you taking your screen, for example, and looking really close at it so that you can see the individual pixels that make up that screen. It's the same sort of concept for a billboard here. So like we said before, just to bring this idea back to the screen, this projector itself, this is made up of only 1,000 pixels across. And in fact, standing right here, it's very easy for me to see the individual pixels that make up each of the, well, that make up the entirety of this image. But perhaps sitting where you are now, it's not quite as easy to see those pixels. It's the same sort of concept where not only do we have to take resolution into account, but also the distance, the viewing distance away from that image. But in terms of computers, every time we're talking about resolution, it is an absolute value. So we are saying that, okay, this image here is made up of 1,000 pixels across and 768 pixels up. And that it makes up our image here. Now, when we start talking about creating images, there are, of course, other things as well. So just beyond images and animations, there is another type of multimedia as well. Whereas multimedia is just, it's what it sounds like. It is just multi types of media, whereas it's probably some combination of images and graphics or sound, or it could be any one of these things, or it could be movies, or it could even be something like games. And games, especially 3D games, take this sort of concepts that we've been talking about to a different level. So because they're designed to be to have this sort of 3D perspective to them, generally what they do a couple of things in order to make them the way that they are. So the very first thing is they make a wireframe out of the object. So this wireframe actually defines the edges of this object in a 3D space, very much like we might use vector graphics, for example. And so this uses some math, but more specifically, wireframes tend to use very simple polygons, like perhaps rectangles or triangles most of the time. And so you can see in this wireframe that it's just made up of a whole collection of triangles and rectangles that in combination make up this, what will eventually be a face. And this again is just defined with some math within the computer. And so in order to give some texture, in order to give this face some appearance, besides just a very blocky, very computer-looking wireframe, they do a couple of very interesting things. First, they fill in each of these polygons with some colors, like you can see here. And it's a very basic, it's definitely an enhancement from our initial wireframe, but it still looks sort of silly. Then they apply some additional math to do some nice shading and to smooth out the polygons a little bit to make it look like the face is actually smooth as opposed to just a collection of polygons and triangles and rectangles. And then finally, they actually apply a texture to this image, and the texture is in fact a bitmap. And so they just take this bitmap and they just sort of wrap it around this object that exists, this mathematical object that exists in memory, and the final result is what we see. And so if you ever play a 3D game, for example, and you're playing a character and you go up really close to a wall and you look to see what that wall looks like, you can sort of see that that wall is made up of individual pixels just because the texture that makes up that wall is in fact a bitmap. Whereas all of the shapes within the world itself tend to be more wireframe and therefore are made using more mathematical models. And so those tend to be a bit better defined. The shapes tend to be a bit better defined than the textures themselves. And so this is one of the big distinctions. This sort of defines the way that a number of video games actually look just because of the way that they are designed. And so we can actually take this concept of a wireframe to an interesting, if not very illogical conclusion, and do something like create an actual object out of a wireframe. So this is actually a real picture that exists of somebody that had made a car out of a bunch of wireframes, just to sort of give it the same look as we had seen just a moment ago. And there's sort of, from what I understand about this story, is that they had placed the image on the street, and because it wasn't, it was considered to be a car, but it didn't have the necessary parking permit, so it actually got ticketed or something silly like that. So it's sort of a funny end story for this non-car that looks almost like it's a video game just in an actual picture, even though it is an actual real-life wireframe represented by this car. Okay, so we've been talking about these different ways that we can create images on a computer screen. We might use a bitmap image, which is sort of the simplest way. It's just a collection of pixels defined with a bunch of colors that we can then use to create an image. Or it can be a vector format, which uses a lot of math to define shapes, and we can zoom in very far into that image because it doesn't require any particular resolution. Or we can use a combination of both, like they do in games, to create all of this. But we mentioned before how in order for us to be able to store a great amount of these images, we generally have to compress them to some smaller state. And so there are a variety of compression techniques, but one of the simplest is something known as run length encoding. And so one type of file called a GIF, a GIF file, actually employs this run length encoding, and it's actually a pretty important type of compression that we can use to greatly save the amount of data in an image. So we have here images of two flags. They are on the computer, 300 pixels across by 200 pixels down. And we can see that they're made up of 3 colors. But because they're in a GIF file format, each pixel can actually be represented by a byte or by 8 bits. So just 256 different values for each of these. So if we zoom that for a moment, how big should these images be on disk? So 300 pixels across by 200 pixels down is how many? How many total pixels? 60,000, right. So 60,000 pixels. And if we assume 1 byte for every pixel, then how big then should this image be, more or less, when we're actually looking at it on our computer? So 1 byte for every 60,000, for every of the 60,000 pixels, we would get about 60,000 bytes, right? So just 1 byte per pixel. That's all that we have. So we have 60,000 bytes, or about 60 kilobytes for each of these images, right? And that's not a lot, but also these images aren't very complex. They're not very large. They're pretty simple images. But let's see if we can do a better job than that. So the whole concept of run length encoding is to look at each individual row of pixels. So it looks at the very top row in each of these images, and it looks at the color at the farthest left column of that row. So in the example of the German flag on the left here, we see that we have a black pixel at the very farthest left, farthest top row. And then we say, OK, I'm just going to say in a quantity how many times this same pixel appears in this row. And so it's essentially compressing it based on the length of the row. So we can see here that the entire row is made up of black pixels. So this really compresses down very easily to just basically a couple of bytes, right? The first pixel is a black pixel, and then we can say, OK, repeat this pixel 300 times. And compare that to actually having a black pixel followed by a black pixel followed by a black pixel, which is fine. We can certainly do that. Obviously, that's how we display this, but it's just not very efficient when we're saving it on disk. So using run length encoding, then, we can store all of this stuff down into just a couple of bytes of information for each of these rows. So we can do the same for the next row, which is again black, the next row, which is again black, and then finally, when we get down about a third of the way, does it change? Then we can store the same thing for each of these other rows of color as well. Now, how about the flag on the right? So we're going to use a similar method, but is it going to compress as well, the same, or better as the one on the left? Based on this encoding technique, this compression technique that we had just talked about, will it take more bytes? And I will give you a hint, the colors actually make no difference whatsoever. They could be the same colors in both flags, but they are actually going to be different. Which might be better?
The German flag is going to be smaller.
Right, so the German flag, the one on the left, is in fact going to be smaller just because we don't have to change the instructions quite so often. So with the French flag on the right, we can say, OK, the very top row, very farthest left pixel is blue. OK, repeat that 100 times. But wait a minute, now there's another pixel in this row, it's white. Okay, so use that, repeat that 100 times. Now there's another pixel, and it's red. Use that and repeat it 100 times. That's fine, that's definitely much better than the original uncompressed version, but it does in fact use more data than the one on the left. Yes?
So is it essentially scanning through it and going back and checking if it's already found that color or not before, whether it's already written that information? Or is it each time it finds a new color, it changes and doesn't check to see whether it's already written that, so it has to write it again?
My understanding is that each time it finds a new color, it restarts and begins again. So if we had a repeat in color, so if this wasn't actually a flag and it was just stripes like red, white, blue, so on and so forth, that were maybe a couple of pixels or even just one pixel across, then it would have to reset each individual time. And it'd say, okay, first one is red for a couple of pixels, then white for a couple of pixels, then blue for a couple of pixels, or rather the other way around, blue, white, and red for a couple of pixels each, and then repeat that same pattern.
Is there like a point at which the complexity of colors in the image renders this sort of useless as a space-saving device or close to useless?
Yes, in fact, there is a very good point. There is a very good reason when this particular encoding does not service very well. And that is, in fact, for any image that's very much like a photograph, where each individual pixel is perhaps very similar, but not exactly the same in color as its neighbor. So we can take a look at this image that is of an apple that has a uniform blue background, for example, and there's only so much that we can do to compress this image in this same way, because the blue background is uniform. And so we can say, okay, the top row is all blue pixels. The next row is all blue pixels, so on and so forth. But we start to get a problem when we approach the apple itself, because each individual pixel might actually be changed ever so slightly from the adjacent one. And so when we actually have raw images or photos, then this same idea doesn't actually work quite as well. And in fact, this type of compression is in fact a type of compression that's known as lossless. All of the data that we're saving, the original data that was used to create these images, can actually be recreated from the compressed counterpart. What that means is that by looking at the compressed data, we can then reformat in its entirety all of the original data that made up these images, right? Just because we know for the German flag, there's 300 pixels of black in the top row, then 300 pixels of black on the second row, and so on and so forth. And we can recreate that very, very easily in its original uncompressed format. Now, this is, in fact, in comparison to lossy compression, where it works perhaps a little bit better for a number of images, but we do, in fact, then, it does work better for a number of images, but we're not able to recreate the original image itself. But before I talk more about that, which is actually a different type of compression, I think I saw a question. Did you have a question about?
Yeah, so could you have this .gif file type, maybe you have another file type that does it vertically?
Oh, so instead of having, whereas GIF compresses very well for horizontal bands of color, couldn't we have a different type of file that compresses it vertically? And so yes, we could, but that is sort of an expensive task to compute both compressions and then figure out which one might be the best, unless the person that was encoding it or that was compressing it knew the difference between the two and was able to then make a distinction. That just adds some additional complexity. We certainly could do that, but it just adds some additional complexity, and for whatever reason they decided to go with horizontal run length encoding rather than vertical encoding. So all of this is how a GIF compresses its data. But we've already talked about how a GIF also only has 1 byte of color for every pixel. And so a GIF might not be the best choice then for something like a photograph, just because there's very subtle changes in color, and even though the colors might appear to be the same, they are in fact ever so slightly different. So as soon as we start getting to images that look like this, where there's much more complexity within it, there's a lot of different colors within an image, and we actually have to compress it in an entirely different way, we'll realize that if we use the same run length encoding for this, we're probably not going to save very many bytes at all. In fact, the only bytes that we might save are going to be in these sort of overexposed areas of the image, where over here where it's like obviously very, very white in this little patch of water right here. But other than that, there's not going to be a lot of capability for us to compress this. So how then are we able to compress an image, an actual photograph, in a much better way without sort of losing too much data? Well, in order for us to talk about that, we'll have to take a 5-minute break. When we come back, we'll continue talking about image compression. Hello everyone, welcome back. So before the break, we were talking about compression of various types and how GIF uses run length encoding, which is a lossless compression type, so that we can recover all of the data original to the image. But if we want to do something like actually encode an image, an actual photograph, then typically we have to employ some more advanced compression techniques. And so going into the how, say, a JPEG actually works is it's actually pretty complicated. But basically, it divides an image into a variety of blocks, like you can see here in a very badly compressed JPEG image here of the same crop. And it will analyze each of these blocks and try to simplify it in some way. And so if you actually look at some of these blocks long enough, you'll actually notice that some blocks are missing color, for example. And so the block that is right here, directly to the left of the bill of the hat, this is in fact a block where they've just thrown out the color, because the compression, the compressor itself has detected that most likely people aren't going to see color in this region quite as well as they might see color in other regions. And so there's some assumptions that go into compressors like the JPEG compressor, a lossy compressor, where it will actually throw away data that it deems unnecessary to the image. And most of the time, this data is imperceptible. When we throw it away, it actually doesn't matter so much when we're actually looking at this image, but throwing away even small amounts of data in specific regions can actually add up to huge savings in the overall JPEG image. So we can actually remove, even at a relatively high quality, we can compress a bitmap image, an original bitmap image, down to just a few megabytes in size when it was originally perhaps a couple of dozen megabytes. But this was, in fact, a lossy compression. What that means is that we cannot, in fact, retrieve the original version of that. Every time we save an image as a JPEG file, we are in fact lossy compressing it just a little bit, and so it is throwing away some bits of data. And so it's generally not a very good idea if you're making lots of modifications to a JPEG file. It's generally not a good idea to modify a JPEG file, save it, and then reopen it, and then modify it a little bit more, and then save it, and then reopen it, because eventually you're going to start losing more and more bits away from that image. Yes? Right. The difference between the two is that the one on the left is basically an uncompressed or it's a losslessly compressed image, so we can see all of the individual pixels as it actually was taken. But on the right, this used the lossy compression, but again, it's over-exaggerated just so that you can see the existence of the compression, because JPEG is actually pretty good. And there's a reason that it's one of the most popular image file types around, because it does compress very well, and the data that it does throw away, generally we don't miss very much. But it is, in fact, lossy. And what this means is that if you overdo it, like we did on this right image here, then you will, in fact, pay the price in quality in your image. So you don't want to go overboard with the compression, because you can, in fact, get what are called lossy artifacts. You can see artifacts as a result of the compression. There's the spray of water has become kind of smudged, and we've lost color in certain regions, and we've lost definition in others, and there's just a variety of things that actually change the way this image actually appears, even though, and again, this is an over-exaggeration, so had I used a lossy compression but not overdone it quite so much, then perhaps it would look a little bit better, or a lot better, and match more closely the uncompressed or the losslessly compressed image. But it is, again, important to realize the distinction that if you lossy compress something, then if you overdo it, you can throw away data that you did not intend to do. Once that data is thrown away, unless you have the original copy somewhere, then that data is gone. You cannot recover that data that you have thrown away in this lossy compression. So this is, in fact, sort of an important takeaway from this is that if you end up modifying, say, your JPEG files, let's say you take files photos with your camera and you take them into JPEG file formats, and you like to do a lot of modifications to your images, one of the things I recommend is, in fact, saving an original copy of that JPEG file. Because once you make some modifications and save that file and make some more modifications and save that file, save it as a new JPEG file and keep doing that cycle over and over, you can eventually degrade the image. And this is not the same thing as opening a file and then saving it without actually performing any modifications. The compression is it's not random in the sense that it's just going to pick random things to throw away. You will in fact sort of get the same file over and over, but it is sort of a warning that through lossy compression you can degrade the image over time in certain circumstances. Yeah.
What would you save that original file as, a TIFF or what?
So I would save the original file in whatever format the camera gave it to you as. So if you download the image and it's a JPEG, that's as original an image as you possibly can get out of your digital camera. If you're going to modify your image a lot, which you certainly can and should do, then you can do that, but just work on a copy of that file. Don't work on the original one, just in case you do want to revert back. It's going to become very difficult, especially in a JPEG, once you make even small modifications to a JPEG file, to go back to the original image. In fact, and we talk a lot about this in E7, one of the things I recommend most, in fact, is in a digital camera to take the raw files, just because that is completely like untouched. It's not even, there's a lot of processing that occurs to an image in a digital camera, even beyond this JPEG compression to create a JPEG image within a digital camera. And saving the raw file allows you even more leeway in the data that is preserved. But that's sort of an advanced thing where you don't really, if all you're doing is just taking photos, downloading them, and sending them to your friends and family, then that's not something you necessarily have to worry about. It only when you start doing lots of modifications to your image, or even some modifications to your images, do one of these other file types become quite handy. Did I see a question somewhere? Nope. Okay. So we've talked about a couple of different file types. So let's then put perhaps a little bit more data behind each of these. And so realize that there is a type column here. You can see that it's either raster or vector. I've been using the term bitmap to mean raster, and it's really kind of the same idea, the same concept in this case. So a raster type is basically just one of these images that takes a bitmap, so a map of individual pixels, and perhaps compresses it in some way. And these are perhaps some of the more common ones that you would see for each type. So in bitmap section, we would have JPEG, GIF, and PNG. And recall that there is, in fact, a bitmap file type, and that is a very literal file that ends in .bmp. Usually Windows machines work with it, but that is pretty much completely uncompressed, and it is exactly what it sounds like. That is pretty much the most raw bitmap that you can possibly attain from an image, and but that's not shown here just because that's uncompressed, and you don't typically see those all that often these days. So JPEG, for example, that's the one that we've been talking about. This is the most common file type that you will see for images, but it is in fact lossy compressed. So what this means is that the file size will be very small indeed, and it will be very fast and very easy for us to transfer an image from my digital camera to my computer to my friends and family, but we are in fact throwing away some data for this to happen. And compare this to, say, PNG or GIF, which are not in fact lossy compressed, they're losslessly compressed. But notice that GIF, even though it's losslessly compressed, you might say, oh, I might want to use GIF for my images. Realize that that might not be such a good choice, just because of the quantity, the bit depth of the individual pixels in the GIF. There's only 8 bits. And what that means, again, is that you can basically only have 256 discrete colors within that image. And to be a little bit more clear, while the image itself can only display 256 different colors, you can actually choose a palette. So you can actually pick which 256 it will actually display, but still we are in fact limited to 256 discrete colors within one image in a GIF file. And PNG sounds like it's sort of the best of all worlds, right? Because it is not only 24 bits, so it will actually display the colors in an image properly, but it's also losslessly compressed. The problem with this is that lossless pretty much always is going to result in a file that is bigger than a lossy compressed. Just because with lossy, you can throw away bits that you don't need, and you can compress it very, very small. You can compress a very large file down to a very small file, and so we then get PNG files for the same image are going to be a bit larger than their JPEG counterparts. Now there's a final column on the far right called alpha. This basically just means whether or not there's transparency within an image. All images are rectangular that you see on a computer. So all of the images that you've seen, I mean, especially out of your digital camera, they're obviously rectangular, so on and so forth. But you can actually make them appear as though they're, say, circular by making some subset of those pixels transparent so that then whatever's underneath will actually shine through. That's all that alpha means. Alpha just means if there is some transparency available in this file type. So GIF does actually support transparency, and this was very famous or a very well used file type on the internet for a long time, mostly because of this transparency issue. You could do some interesting things where you could create, say, a border that had a rounded corner, for example, and then you could make around that corner transparent, and so on a web page, that GIF file would look as though it were creating this sort of nice rounded border on that web page. Nowadays, you will tend to see PNG used instead, just because now it does support a lot of colors, it's lossless, and it also supports alpha. But the tricky thing about PNG is that some older browsers do not actually display the transparency properly. And so the final file type here, EPS, this is one that you're not going to see very much, but it is an example of a vector file type. It is something that if you were to download a vector file, it might come in the EPS file format. Now, let's see. So with each of these, realize that all of this is all the different types of files that we can actually store an image in. And so we can actually store an image of arbitrary size, say 300 pixels by 200 pixels, as it was the case of those flags, or even an 8 megapixel image in any of these file types here. And really depends on the size. So the reason that you would pick a different file type, you generally want to pick the one that's going to be most appropriate for the output of your image. If you are using an image from a digital camera, then most likely you're going to want to use JPEG, just because that's very, very popular. Pretty much everybody that has access to any sort of computing device, even phones, have the capability to even, I don't even mean fancy phones, I mean like simple phones, generally have the capability to display JPEG files. And compare this to some of the other file types that are perhaps not well suited for something like digital photos. But there is one more thing that we should talk about with regards to images, and that is the size of the image itself. So we've talked about how before, when you can have an 8 megapixel image and you can display it on your screen, and if you display it at 100% and your screen resolution is not quite as large as the resolution of the image, then what's going to happen is you're going to have this annoying size difference. You'll see only a corner of that image, and you're going to have to zoom out a bit to be able to make that image display properly on your screen. Well, realize that it's actually a very useful, very important thing whenever you download an image from your, say, digital camera or from the internet, and you want to send that along to somebody else. Generally, the nice thing to do, the good thing to do, is to resize that image so that it's appropriate for somebody to look at. And generally, this applies mostly to digital cameras, because digital cameras tend to have way too many megapixels that people don't even use most of the time, especially if what you're doing is sending an image from your computer to your friend or to your family. Then what the best thing to do is to resize that image so that when they look at it, it doesn't inundate them. It's not huge on their screen, but perhaps is sized to fit a little bit better. And so while you're not going to obviously be able to target a resolution because you're not going to know what everybody's resolution is going to be, generally having something in the range of, say, 1,000 pixels to maybe 2,000 pixels wide is generally a good target for your image if you're going to send it out. And so the reason for that is that most displays these days are in the range of, on the lower end, 1024 by 768, as is in the case here, and they go all the way up to 2000 or so on the very large 24, 30-inch display monitors. And so that's sort of a good resolution to pick when you're trying to decide how to resize your image and send it out to somebody else, just because then they're most likely going to be able to view that image without that annoying, without having that annoying way too large for the screen. And the other upside is that resizing the image actually goes a long way to modifying its size on a disk as well. So it will also upload more quickly and it will download more quickly from your computer to your friends or family's computer. Now there's a variety of other multimedia types as well. And in fact, audio is one that has been sort of controversial, especially a few years back, and it continues to this day, where a variety of file types have actually made it very easy for us to store audio in a very, very small way. So uncompressed audio actually takes up quite a lot of space. I think it's, let's see, what is it? So CD has about 800 or 700 megabytes or so of space on it, and they're generally about 60 to 70 minutes. So we could say then generally that in uncompressed audio, CD quality is going to be about 10 megabytes per minute. And that's quite a lot. So if you start saving some songs onto your computer and they're just maybe 3-4 minute songs, something like that, then we're talking about 30 or 40 megabytes just for one song. And this is uncompressed again. And so there's the same idea of having different types of files that are compressed in different ways so that we can then store these same files in a much smaller way on our computers. And the most popular one, obviously, is MP3. This is the one that everybody knows about, but this is sort of analogous to the JPEG in the audio world just because it's very, very popular. Pretty much every computing device can interpret and play an MP3 file, and it's lossy compressed. It throws away data that the encoder doesn't think we're going to be able to hear. And so it just does this based on some heuristics, based on some research that the company that created MP3 decided, okay, well, we're not going to actually need to play sounds in this frequency or within this range, or sounds that look, or sounds that appear in this sort of range are just not going to be necessary because most people are not going to be able to perceive them or hear them. It throws away those bits and it makes those sound files much smaller. So there's a variety of different file types. WAV, WAV, AIFF, those are all uncompressed file types, and those are going to be absolutely monstrous, massive. Lossy, compressed, MP3 is one of them. AAC is another one. Apple tends to use quite a lot of AAC in their own, in iTunes and in their own iTunes store. And those are, in fact, I think generally for the same size, I believe people say that AAC tends to have slightly better sound quality than MP3 for the same size file. Losslessly compressed, these are not quite so popular just because they still result in quite large ones, but FLAC, F-L-A-C, is a pretty popular one. AAC also does have a losslessly compressed format that you can do, but generally when we see AAC, it is in fact lossy compressed. And there's some other less popular ones like OGG, which is in fact lossy compressed, and some other ones that, that do in fact make up a variety of audio formats. But realize that there's even more than just these sorts of formats where we can take an actual song, some actual sound, and compress it down to some smaller format, and then the computer will actually be responsible for decompressing it and interpreting the bits and playing back the original song file itself. There used to be, especially in the earlier days of the internet, a much simpler type of sound file. And I realize that this is not quite as visually exciting to look at, but bear with me for a second. We do have two sample sound files here. One of them is a file type MP3, I think, or it's at least some sort of regular compressed format that we are familiar with. And what this does is it's just a segment of Mozart's 40th, I believe, if I remember correctly. And it sounds like this. It's basically what we would expect from an MP3 file. It sounds like it's an orchestra playing. It's some recording of an orchestra that is played at some point, and we've compressed it so that we can then hear it at a later point. Okay, so this is common. This is nothing new, hopefully, to all of you. If any of you are new to MP3, I recommend opening up your web browser and looking around on the internet. It is very popular these days. Now, one of the older formats, though, was a MIDI file. And a MIDI file was actually very, very small. It was not even compressed very much, but just because it didn't have to be. In fact, if we take a look at the difference in size, you might be actually kind of surprised. So realize that we have, okay, so it wasn't in fact MP3 compressed, it was compressed using AAC. the symphony number 40, the one on the bottom. And then the one on top is, in fact, the MIDI file format. We can see the difference in size. 15 megabytes as opposed to 90 kilobytes. And so I always get annoyed when people put things, they always put comparisons of numbers in different powers like this. So just to make this real, this is 90 kilobytes, and we have 15, it was 15, right? 15,200 kilobytes. So just to give you an idea of the difference in size, we're talking about quite a lot. But you must be saying, well, okay, we probably have to sacrifice quite a bit of data then in order to achieve this compression. And in fact, realize that this is not, in fact, a compression, but what it is something else entirely. It is, in fact, just instructions to the computer telling it to synthesize the notes. It's just a collection of instructions, just a collection of notes within this file that says, okay, play this chord and then play this chord. And this instrument, you should play an instrument that sounds like a violin that plays this note at this time, and that sort of thing. So it basically is sort of like the equivalent of sheet music for a computer. And even though a computer is then able to create sound like this, it obviously sounds synthesized. And so this was something that was very popular back in the days. So I'll just let you listen for a couple of seconds so you can sort of get the idea. Unless any of you are tearing your ears out by now just because it sounds so awful. Well, this was in fact something that was, like I said, popular early on in the days of the internet, just because this was how somebody could create some music and send it to other people, because 90 kilobytes is a lot easier to send than 15 megabytes of data, especially over old dial-up connections. So it downloaded much more quickly and it was much more popular. But obviously, this didn't take off in modern times for obvious reasons. It's just not, there's no support for vocals. There's no way that even within different computers that it's guaranteed to sound the same. In fact, if you put this on your own computer, your computer might synthesize the sounds a little bit differently. It might sound better, might sound worse. It really depends on your own MIDI synthesizer. So realize that there are, in fact, other types of media as well. So video now is a sort of a compilation of all of these things that we've been talking about. It's obviously a collection of pictures that are then displayed one after the other to give you the sense of motion. And then it also generally tends to include things like audio as well. Well, video is actually it's a pretty complex topic. It actually builds upon a variety of things that we've talked about now. And so a video file generally is just a container. So it looks sort of like this. Well, it doesn't look like this, but this is just sort of an analogous representation of what a video file might be. It's just a collection of files contained within it. You're not going to be able to see what these files inside of it are, necessarily what they're named, because they're given a very strict, they're named very strictly, and it's not really this idea of having files that you could put into a video file and take out. But this analogy does in fact stand, where you could have a package or or just this sort of wrapper that exists around a variety of different files, and whose in conglomerate makes up this video file. So one of these things might be a sound file. It could be an MP3, or it could be an AAC file that's used to represent the soundtrack of the movie, or actually all of the voices and the sounds that make up this video file or this movie might actually be within this sound file that's contained within this container. Then you might have another thing altogether, which is the video itself. And so you might be familiar with some of the names of some of these wrappers, like a .mov file, for example, or a .avi. All of these are just names of wrappers or packages, containers that contain a variety of other files within them. So AVI is one of them, for example. MOV is a QuickTime file type. MKV is sort of kind of popular these days. Let's see, RM, which luckily we're not using very much anymore, for real media, real player, that sort of stuff. And all of these contain within them probably something like you can think of it like a video file and kind of like an audio file as well. And so each of these wrappers then might have some different type of file contained within it. And you might have heard of some of these codecs, these compressors, decompressors that actually make up some of the video files. So one of them is like DivX, for example. Another one that's very popular these days is H.264. And these are just technologies that compress video itself. And generally, some or all of these packages can actually contain these different types of video encodings. And so again, this is really just this idea of a container where they define in some way, in a movie file, for example, where each of these video portions and audio portions are going to exist within the image or within the file itself. So this is the containers, and this is the video codec. And again, a codec is just a compressor, excuse me, compressor or decompressor. It's just a way that a computer is able to compress the video into a known format, just like we have this concept of run length encoding in GIF versus this sort of blocking format that they use in JPEG. And there's also audio support as well. And generally, you would see common audio types like MP3 or AAC or some other different audio types that might be in existence, OGG, for example, like the Aura. And all of these might be in combination with some portion, with some video that's compressed in, say, H.264, in combination with perhaps some soundtrack that's compressed in MP3. We can actually fit both of those in some file that's labeled .mov. So what does this mean then? Why is there all of this complexity? Well, realize that if we just have a video that looks sort of like this, and we actually look at the contents of that video, we can see a couple of interesting things. Realize that looking at the format of this video, we see a lot of really interesting things about this file format itself. So this is, in fact, Cars 2 trailer. And if we look at the source portion right up here, the first line that's in bold right there, we can see that it is, in fact, a movie container, .mov. So this is a QuickTime file that contains within it some audio and some video. Just because if we start playing this, we will, in fact, see that it is playing some audio and video after this thing plays for a second. So here, all right. Right, audio and video. So you can see both at the same time. So there's obviously something that combines this audio and this video. And that is what we are looking at right here. So within this movie file, this .mov file, we have a couple of things. And those couple of things we can see in format. One is H.264. That is the video codec for the video that's actually playing on your screen. We can actually see some other information about it. 1920 by H16, millions. So based on the discussion that we've had so far today, what does this stuff mean? What does this information mean? Besides H.264, what is 1920 by 1816? The resolution. So this is, in fact, the number of pixels wide by the number of pixels tall that make up this particular image. Now, what about millions? Yeah, colors. So that's how many colors we have. So in fact, most likely then, this is a 24-bit color because it has millions of colors, and we have 1920 pixels across by 816 pixels down. Now, AAC, this is, in fact, like we talked about in audio format, 2 channels. We didn't really talk about channels, but that just means it's stereo, left channel and a right channel. You can see there's this mysterious hertz thing again, but again, this just references how many cycles per second or how many samples per second we actually have for this particular sound. Now, there's a couple of other interesting things as well. FPS, that's the number of frames. That's the number of images that appear in this video file per second. And generally, for anything that is film related is almost always going to be 24 frames per second. Anything that's film is going to be 24. Generally, things on television are about 30 frames per second, unless you happen to live in a country that uses the PAL type, which is then, I think, 25 frames per second. And so there's a couple of different common frames per second that we might actually use. Now we can see the data size. The size of this entire thing is going to be about 152 megabytes with the data rate. We can actually see the current size. So this actually highlights what I had mentioned before. What happens if we actually have an image that's too big for our screen? 1920 is too many pixels for the resolution of this projector. Remember, this projector was 1,000 pixels across, 1,024 pixels across, which means that if we viewed this video at full size, we would be missing half of it, just because half of it would be on screen and half of it would be off screen. So what we have to do then to actually display this video properly is to try to resize it to fit the screen. So we can do that just like this. Did I see a question before? Yes?
What does that say under AAC? No, on the Blackboard.
Oh, on the Blackboard. Under AAC, OGG, that's just a file type called OGTheora. It's not as well known, but still among geek circles sort of popular because it's sort of an open source format, I believe, for audio, as opposed to MP3, which I think, at least for a long time, was closed source. They did not actually, or it was at least, it had restrictive licensing, I think was the problem. And it's sort of a similar thing now with H.264. And Google has recently come out with another file type themselves, which is, shoot, I'm blanking on the acronym. It's something like VPM or something like that, where it's supposed to be this license-free version competitor to H.264, which they're using now in their own Chrome browser. Any other questions? So there's a couple of other wrappers as well that we might actually be familiar with. One of them, or you might actually, it's okay if you're not too familiar with it, but you have probably used it at least. Another one is SWF, or the Flash file type. And this is just a container that can contain a variety of things. One of them, some Flash containers can actually contain H.264. So if you go to YouTube, for example, and you're watching some YouTube videos, chances are you might actually be looking at a video that was encoded with H.264 and probably either MP3 or AAC for the audio, but contained within an SWF container. Now there's other ones as well. MP4 is sort of another common one. It's almost interchangeable with MOV. I'm just sort of listing these so that if you start to see these online, they will hopefully make a little bit of sense. Realize that MP4 is sort of confusing because it's not necessarily related to the MP3 audio. It's just meant as a container which can contain other formats within it. Now when we're actually compressing video, this actually can be quite a complex thing itself. And so there's a couple of different methods that we can use. We can have interframe compression, or we could have intraframe compression. And so the one that we use depends on basically what it is that we're looking at. So if we are looking at, say, interframe compression, then what we are going to be doing is compressing between frames, so between multiple frames. So what we have here, for example, is an image of a bee that sort of buzzes across a static background. This might actually be a good way for us to compress. What if we can actually remove the background? We can find out that between multiples of these frames, in interframe compression, then what we can do is notice that the background is actually identical. We can actually remove it. We can actually say use the same background from the previous frame, but now change only these pixels so that now the bee appears as though it is moving, and we can recreate the original scene as shown at the very top. But what we will do, what the end result will be, is that we can save far fewer pixels just because we don't have to know then all of the bytes that were used to make up the background of this particular video file. Now, another type of compression might be something that looks like this, where it basically just records the changes. This is sort of a similar idea where it just records the changes of each of the frames from the previous one. So that it says, okay, well, based on this frame, these pixels change in some known way, like this. And so then the decompressor then has to look at that and say, okay, I'm going to display this image and change these pixels. And compressing video is actually far more important, I would say, than compressing audio or images. Just because, and if we think about this for just a second, if we use something that's about DVD resolution, so we have an image that's about 720 pixels wide by about 480 pixels down, and it's at a standard film resolution, or standard film frame rate per second of about 24, multiply that by 3600. So what that means is that we have 24 of those 720 by 480 frames, 24 times a second for every second in an hour. Then uncompressed, we're going to have about, I did this math before, 27 gigabytes of data, more or less. And that's quite a lot of data. And that's not even HD. If we start talking about HD, which uses something like 1920 by 1080 times 24 frames per second times 3600, then what we get is something much, much bigger, something like 170 gigabytes just for an hour. And this is a lot of space just for an hour worth of video on your computer. And this doesn't even count the audio. So just for the video itself, we are talking about enormous quantities of space. So being able to have good compression techniques is something that is pretty important. And right now, some of the most popular, in fact, H.264 is sort of the popular way of creating HD video, just because it is very good at some of these techniques that we're showing here. Just because it does it relatively efficiently, it can create a relatively small file and maintain very, very high resolution. And in fact, looking at this same trailer once again for Cars 2, we can see that it is in fact at HD resolution. So realize that when people are talking about HD, they really are just referring to a set of resolutions or a set of known resolutions that video files should fit in order to be called various levels. So there's a couple of different types of HD. So sort of the lowest one is 480p, then there's another one of 720p, and then there's another one with, or no, not 1920, that's the horizontal resolution, 1080p. So these are sort of the common terminology that you might see for HD video. And luckily, this terminology is used not only in the context of televisions, but also in computers and in videos all over the place, really. And so if we're looking at this video here is actually fits within the 1080p resolution. So the maximum resolution for each of these is as follows. So for 1080p, all of these actually represent the number of horizontal lines. So that's sort of the easiest way to remember this. So 1080p, we have a 1920 width by 1080 pixels down at a maximum. 720p is, I think, 1280 by 720, and 480p tends to be something like, let's say, I think it's about 854 or 720, depending on the aspect ratio, by 480 pixels. And so 480p tends to be the resolution of DVD players, just to give you a concept of this, whereas full HD, you know, that terminology that people love to use, actually represents 1080p. So this is full HD, but 720p is actually considered to be HD resolution as well. So people go nuts over these resolutions. They say, oh yeah, this is such high resolution, I can see all the detail on them. And yeah, you know, it's definitely an improvement over what we had in the past. But honestly, we've been running these sorts of resolutions on our computer screens for a long time now, and only recently has the technology sort of caught up so that we can now actually display video at that high resolution. Just because there's so much data, if we're talking about 170 gigabytes or so of data every hour just for video, that's a lot of data to process when displaying some video for us on the screen. And so there's a good reason why HD has sort of been elusive, just because there's a lot of data for us to crunch. So when I downloaded this trailer, I actually downloaded two versions. There was this version, which is the 1080p version, and also the older version, or rather the DVD quality version, which looks like this. And now realize that there's something kind of interesting here, and that is that the DVD quality version actually fits pretty well within this screen. So this sort of just goes to show you that if you are looking online and you want to just default to always using the highest resolution video available, realize that you may not necessarily have to, especially if you are on a laptop, for example. Many laptops don't have high enough resolution to actually display 1080p on their screen without having this annoying problem of having to resize the image, which can be, you know, a drain on your computer's resources. It's just sort of unnecessary to display it if your computer or if your television does not have the resolution, the capability to display such a high resolution on its screen. So yes, it is in fact a noticeable difference, I think, especially from the earlier forms from DVD forms or from early SD, as it's so called, broadcast forms of television, but you have to have also the technology to be able to display it, I think, properly, so that you can actually take full advantage of all of the resolution, of all of the pixels that's available to you in such a high data stream. Any questions on any of that? Okay, so just to compare these two files, we can actually look at this file as well and just notice that the size itself, the size in pixels, is actually much smaller. It's 848 as opposed to being 1920 by some number of pixels. But we can also see that the data size itself is much, much smaller as well. So this is about 40 megabytes. Compared that to the Super HD version up here, which is 151 megabytes. So there's this trade-off. Yes, you're getting a lot of additional detail in this higher resolution, but you're also sacrificing quite a bit of size in this data. And you can also take a look at this data rate. This is the amount of data that on average, that your computer has to process in order to display this image. And so what this is saying is that, okay, every second it has to process 9.31 megabits so that it is able to show this image on the screen. And that might not sound like very much, but because H.264 is so heavily compressed, there's actually a lot of computation that it has to do on these 9.31 megabits. And compare that again to the data rate here, it is just much smaller. It's now about 2 megabits per second for this lower resolution version of this same thing. And this is why, if you're trying to watch video that's very high resolution on your computer and sort of stuttering and it's dropping frames and it looks like it's very jittery, then this could be a reason why your computer just may not have the capability to process so much data and display all of these pixels and go through all of this audio at the same time to display it to you at the end. So with many, now it's sort of nice now that a lot of TVs now especially use the same sort of terminology, because now we can start using the same terminology not only for our video files on our computer, but also on TVs as well when we're talking about HD resolution and all of these different types of data. Now finally, of course, there are all of these videos are in fact tend to be encoded in some way, but they're also encrypted in some form. Usually they have some form of digital rights management, some DRM in other words, that are applied to it. And this really is sort of it's an always ever-present controversy, it seems, with media, especially a few years ago. The whole MP3 thing that happened, that went down, and still to this day is the recording industry still finding people that are sharing MP3 files and suing them for lots, huge sums of money. And now sort of the same thing is going down with the movie studios as well, where they're trying to find people that are sharing these movie files. So just because it makes it very easy, in fact, to share these bytes of data, just to share all of these bits of information from one computer to the next, doesn't mean that you'll be able to necessarily get away with it. But just realize also, I think it's sort of an interesting concept that will have to be resolved eventually. I mean, it makes all of our computers make this so easy for us to be able to copy data from one computer to the next. And so what is going to be the end result of this, of sort of all of this stuff that's going down between the RIAA and the MPAA, the Recording Industry of America and the Motion Picture Association of America, respectively? What is actually going to happen with all of this? And it's something that we'll have to watch out for, but just take care. If you are online and you're trying to download some videos, make sure that you are not necessarily you're not infringing anybody's copyright, because that could be something that's sort of a silly, bad thing for you to do, even though it seems like very many people are doing it these days. It's just sort of something to definitely watch out for, and especially on things like YouTube. There was a whole debacle a few years ago where YouTube got sued. YouTube and its parent company, so now it's owned by Google, were sued by Viacom for having placed some infringing copyright material up there, even though YouTube had nothing to do with it. It was just their users. And so what constitutes sort of this acceptable use? Can users do this? Does YouTube have to be responsible for policing this data? It's sort of an interesting thing, and there's a lot of controversy going on in other countries as well. I think France might have recently passed, or they were considering passing a law that said you have basically 3 strikes. It's this so-called 3 strikes law, where if you're caught downloading illegal content 3 times in a row, no trial, no nothing, you are without internet access. They cannot legally give you internet access or something like that. So it's going to be interesting, I think, to see how all of this plays out in the next few years. And I'm not saying that this is necessarily something that the average person has to worry about, but if you are doing this, and it is something to watch out for if you are, in fact, doing this sort of sharing of copyrighted content. And for now, that is all we will say. But join us next week when we are going to start talking about security and start scaring you all again with some of the stuff that can happen on the internet and to your computer. So until then, thank you all for coming.